Welcome to Ask and Learn.
So this problem is about a dipole, and we have the coordinates of the two charges. So one of them is here. This is minus 1.2 millimeters and 1.1. This is the positive charge, 3.5 nanocoulombs, and the other one is somewhere about there. This is 1.4 minus 1.3. So the dipole moment is going to be the charge times the vector between them, which points like this, from the negative to the positive. So this will be, if we break it into components, we can say the x component times I hat plus the y component times j hat. Now the charge is 3.5 nanocoulombs, which is 3.5 times 10 to the minus 9 coulombs. And okay, so the x component, we can subtract the two x coordinates, and in millimeters, this is going to be minus 0.0012 minus 0.0014, and then do the same thing over here. For the y coordinates, we can say positive 0.0011 and minus a negative 0.0013, and this is the j component, so we get minus 9.1 times 10 to the minus 12 I hat plus 8.4 times 10 to the minus 12 j hat, and this is the dipole moment, so it's coulomb meters. Now the torque on this in an electric field is going to be the dipole moment crossed with the electric field. And this is the dipole moment we just found up here. And the electric field is given as 7.8 times 10 cubed I hat minus 4.9 times 10 cubed j hat, and this is in newtons per coulomb. So to take the cross product, we can set up a matrix, a 3x3 matrix, where we have I hat, j hat, k hat, and then there are no k components to start, so we can plug in the x and y components of each vector. This is 9.1 times 10 to the minus 12 and 8.4 times 10 to the minus 12. And then the field components. Now to take the cross product, there will be no I or j components because of the zeros. So the only part we get is a k hat component, and then we're going to multiply these two. So minus 9.1 times 10 to the minus 12 times that, and then subtract this product going the other way. And then this whole thing is the k hat component. So we get something negative. We get minus 2.09 times 10 to the minus 8. And this is in the k hat direction, and we're in torque, so it's Newton meters. Now the potential energy of this system is going to be negative the dipole dotted with the electric field. So let's write out these two. This is minus 9.1 times 10 to the minus 12 I hat plus 8.4 times 10 to the minus 12 j hat. And we're dotting it with the electric field now. So 7.8 times 10 cubed I hat minus 4.9 times 10 cubed j hat. Now to take the dot product, we just multiply these and add the product of the second two. So we get minus 7.098 times 10 to the minus 8 minus 4.116 times 10 to the minus 8. And this is a scalar. And these two sum to negative, and then we take the opposite of that, so we get a positive 1.12 times 10 to the minus 7. Now, the difference between the maximum and minimum energies, well, the maximum energy, actually both the maximum and minimum energies are going to occur when the dipole and the field are parallel, but the maximum is going to be when they're in opposite directions. So we can take minus PE, and then the angle between them is 180 degrees. And the minimum is going to occur when the angle between them is 0 degrees. So cosine 0. And cosine 180 is minus 1, so this just goes to positive PE, and then these negatives will cancel out, and cosine 0 is positive 1, so this is plus another PE. So we get 2 PE. Now, the magnitude of each of these vectors, in order to get those, we need to take the square root of the sum of the squares. So take the x component and the y component, add them together, squared, take the square root, and do the same thing for the electric field. So this is going to be minus 9.1 times 10 to the minus 12 squared plus 8.4. And then take the square root of that whole thing, and then do it again. 7.8 times 10 cubed squared plus minus 4.9 times 10 cubed squared, and multiply all that together, and we get 2.28 times 10 to the minus 7. And these last two, they're both energy, so that's in joules, and this is also in joules.